the spin of an electron cannot be due to the rotation about an axis in a physical space. Let me explain why. The angular momentum we can write as I into omega, where I is the moment of inertia, and the spin angular momentum is of the order of the reduced Planck constant. So if I substitute V and R, here R I have taken 10 to the power minus 15, you will get velocity of the order of 10 to the power 12, which is much greater than the speed of light, and it is not possible. So the spin of an electron cannot be interpreted as the rotation in physical space. Then what is this spin? Normally we limit ourselves by saying that spin is an intrinsic quantity. So from where this intrinsic quantity arises? That is what we are going to discuss in this video. If you consider an electron revolving around a nucleus, we need to treat this system with quantum mechanics. In quantum mechanics, we talk in terms of probability. And we solve the Schrodinger equation, which is the equation of motion, and we try to find the wave function. This wave function is the probability amplitude. It's a complex value function. Now, this wave function, it tells us where a particle might be or how fast it might be moving or how it might behave, but not with certainty, only with probability. And the square of the wave function gives the probability density. Now, coming back to this example, an electron revolving around a nucleus. The diagram which I have drawn, here we have a well-defined circular path, but when we treat it with quantum mechanics, the path cannot be well-defined. So instead of this, we show it with a electron cloud. Now the next question is, where does quantum mechanics plays out? In which type of space? Like in classical mechanics, we use the space-time physical space to analyze the mechanics. For quantum mechanics, we use an abstract space known as the Hilbert space. Now, this space allows us to represent the quantum states in terms of a vector. By the way, when I say vector, this vector is not same with the usual vector which we come across in classical mechanics. And the probability is given by the inner product of this quantum states. And all the measurable quantities like energy, spin, angular momentum, all those quantities can be obtained by taking an appropriate operator acting on the quantum states. Let us consider a system where a ball is falling under the gravitational field. Now, if I observe this system from a frame of reference S1, another frame S2, which is a translation of S1, and a third frame S3, which is a translation and rotation of S1. Now, from this three frame of reference, the laws of physics should be the same, or in other words, the laws of physics should be invariant of the rotation or translation of the frame of reference. This condition is what we call as a symmetry in physics. Now, if I consider a physical space, say a subatomic particle is there in the space, and if I rotate this frame, and the rotated frame is S prime. Now, we know from classical physics that the transformation is given by this relation, where capital R is the rotation matrix. Now, under this rotation, the vectors like position, angular momentum, velocity, all these vectors should transform in such a way that the physics remain invariant. Now, what about in quantum mechanics? We have already learned that quantum mechanics plays out in Hilbert space. So, if there is some transformation like rotation in Hilbert space, so how the quantum states will change? Now, let us consider an old state, and I'm performing some rotation in Hilbert space, and we are getting a new state, let's say psi prime. Now, in these two states, the probability density should be the same, or in other words, the probability density should be invariant under rotation. That means psi prime should transform from psi in such a way that the probability density is invariant. Now we need to find the correct expression that will make the probability density invariant under rotation in Hilbert space. This is what we call as the representation. Representation basically it's how to act on the quantum states when the system undergo transformation. Basically it's a operator that represents rotational symmetry in Hilbert space. So this operator is represented by UR. Here R is the rotation in the physical space. So what is the correct operator that matches the rotation? Now it is found that different particles have different representation, and the type of representation is what indicates the particle's spin. So to keep the laws of physics consistent under rotation in Hilbert space, we need to find out how the quantum states transform, and that is where the spin of particle comes into picture. Now let us consider three examples, one of spin 0, one with spin 1, and the third one with spin half. So for spin 1 particle, the UR is equal to 1. So the new state is identical with the old state. So there is no change under rotation. For spin 1 particle, the UR is equal to the physical space rotation matrix. So the new state will be given by this relation. So it transforms exactly like a real space vector. In the case of spin half particle, the expressions are a bit complicated, but I will not be going deep into mathematics. So the UR is basically a 2 cross 2 SU2 matrix, and the transformation is given by this relation. And in non-relativistic quantum mechanics, we represent the state of a spin by using a two component vector known as the spinor. To get a simplified analogy of the spin of a particle, let us use non-relativistic quantum mechanics, and the UR can be represented like this. By the way, I'm not going deep into mathematics. It's just an operator operating on a spin state. And here ms is the quantum number. So for the three examples, for spin 0, ms is equal to 0. So if you see the exponential part, since ms is 0, so the exponential gives 1. So this means that the state remains unchanged for any rotation of angle theta. What about for spin 1 particle? So ms can have -1, 0 and +1. When we take -1, so we have e theta, which has a period of 2 pi. But if I take 0, then e to the power 0 is 1, so it can have period of any value. But if I take +1, that is e to the power minus theta, then the period will be of 2 pi. Now, we should choose here we have 2 pi and the other option is period of any value. But we should choose a particular time period which works for all the three possible states. So the period will be 2 pi. In the case of spin half particle, ms can have -half or +half. So if I substitute, then it is e to the power minus theta by 2 or e to the power theta by 2. Now this exponential has a period of 4 pi. This is very important because in next slide I'm going to show you a simplified analogy of the spin 0, spin 1 and spin half particles. Now we have established that spin 0 has a period of any value, spin 1 has a period of 2 pi and spin half has a period of 4 pi. Now, using this concept, I will show you a very simplified analogy of what the spin value shows. Now, consider this example. Here, the circular dot in this picture, assume that this is the quantum state in Hilbert space. Now, if I rotate this dot at any angle, it remains the same. So, this is analogous to the rotation of spin zero quantum state in Hilbert space. For spin 1 particle, now you assume that the red arrow shown here is representing the quantum state in Hilbert space. Now, if I perform a 2 pi rotation, it comes back to the original state. That is, it has a periodicity of 2 pi. But what about for spin half particle? For the spin half particle, we need to have an analogy which has a periodicity of 4 pi. There are other examples, but here I'm using one particular one where you have a red arrow in a Mobius strip. Now, the change in the state after rotation is indicated by the red arrow traveling along the boundary of the Mobius strip. So, if I give a pi by 2 rotation, then the state will look like this. Now, if I further give another pi by 2, that is a total of pi, then the state will look like this. Now, if I further give pi rotation, then it will give like this. Now, if you compare the initial state and the 2 pi rotated state, you'll find that the direction of the arrow is different. In quantum mechanics, we say this as there is a phase factor of -1. Even though the probability density are the same, there is a difference in the phase factor. Now, if you go further and add another 2 pi rotation, there is a total of 4 pi, you'll get the final state which is identical with the initial state. That is, it has a periodicity of 4 pi. And this is a simplified analogy of how the quantum state changes in Hilbert space. Thank you everyone for watching this video.